So let's find relative maxes and mins. We have the first derivative test, the second derivative test, and some information about finding the y value. All right, so we have a function for all real numbers, and it tells us that it has a relative max at x equals blank, and that's what we're supposed to find. So let's find the derivative, find the critical numbers where we have horizontal tangents, do a number line test to see if we have a slope change from positive to negative. I'm going to factor out a 3x. Set each factor equal to 0. So x equals 0 or x equals 2. All right, to save time, when you do test values, you're going to get positive slopes. When you do test values between 0 and 2, you're going to get negative, and it's positive over here. So we can see we have a maximum at x equals 0, and we have a minimum at x equals 2. So the question was, looking back, okay, has a maximum a relative max, that's an interior point. Okay, it doesn't say absolute, so we don't have to do a t-chart, but a relative max is going to occur at x equals 0. So I would state f has a relative max at x equals 0 because we're just going to say because f prime changes from positive to negative. All right, look at question number 2. It says find the relative maximum value. Okay, unlike question number 1 where it says it has a relative maximum at x equals, this is the word we want to pay attention to. Okay, that's actually a y value. So we're going to have to find the x coordinate, and then after we find the x coordinate of the relative max, then we're going to have to plug that x coordinate into the original equation to find the y value. So the first step is to find the derivative. When we study the structure of this equation, this function, we notice that we're going to have to use the product rule. This is our first factor and our second factor. So the first factor times the derivative of the second, plus the second factor, e to the x, times the derivative of the first, which is 2x. All right, so we're looking for critical numbers. So set the derivative equal to 0. Notice you can factor out e to the x from both these terms. Okay, and here in the next line I'll rearrange these terms. Set each factor equal to 0. So I'll rearrange and set equal to 0. Okay, now if we think about what this graph looks like, it's always above the x-axis. It's e to the x. It'll never intersect the x-axis, so there's no solution. For the second factor, we're going to have to factor it. And so the two critical numbers are x equals 1 and x equals -3. So if the question had just been find the relative maximum at the x coordinate, then we just do a number line test and see where the slopes change from positive to negative. But because it's asking for a value, once we determine where the max occurs, we're going to have to plug either one of these two, if they do result in a maximum, back into the original function to find the y value. So let's continue by finding the maximum if there is one. So first derivative number line test, let's find a number that's smaller than -3, -5. So I'm coming back up here to this part of the equation. Let's plug in -5. Well, remember, this is always going to be positive. It's just going to be small. Okay. If you were to plug in -5, say in here, which is really this factored. So plug a -5 in here, you're going to get negative, negative, that's positive. So it appears that we're going to have positive slopes here. And to save time, this is actually going to be negative, and test values determine that these slopes are positive. Okay, so it appears that we're going to have a maximum at x equals -3, but then we want to go back and find the y value. So 9 minus 3 is 6. 6e to the -3. You're done. You can rewrite it as 6 over e cubed if you want. Okay, either one will work. So that's actually what they're looking for, is the y value. But we had to find out the x value first. For example 3, this is an interesting problem. It says, what is the minimum value of the function? And then justify. It doesn't give us a closed interval. That's what's interesting about it. But it's basically saying what is the absolute minimum value, y value, the lowest y value. Okay, so it must be that this graph probably dips down and comes back up and never returns down. So it must just have a natural minimum value. Much like if you think about a parabola. So if I kind of come over here and remind us about the parent function x squared. If you think about that for just a minute. Okay. If you're asked to find the minimum value of this function right here, and I didn't give you a closed, or you weren't given a closed interval, it does have one. It doesn't have to be that you have a closed interval to have a minimum value. The graph could just naturally form a low spot. So that must be what's happening here. So what is the minimum value of this function? How do we proceed? Well, we're going to need the derivative, and we're going to do a number line test. You know, the t-chart, you know, we could kind of work with that if we wanted to. So, but we're going to actually end up abandoning that. Something to point out, though, about this function is that for the natural log of x, okay, that natural log function is only defined for x values greater than 0. If you think about the natural log of x graph, I'll put that here. Okay, it has this shape. So we know at least that our answer is going to have to be something that's greater than, our x value anyway, greater than 0. All right, so what is the minimum value? Let's find the derivative using the product rule. First factor here, second factor here. First times the derivative of the second plus the second factor times the derivative of the first. Let's clean it up. So these x's will cancel, so I'm left with 0 equals 1 plus the natural log of x. Okay. All right, so let's solve for x. I'm going to move the 1 over and then trade sides. So natural log of x equals -1. Okay, to get x away from natural log, we're going to bring in the exponential. Okay, so those will cancel. So we have x equals, I know there was an e there, I think it just disappeared. There it is. E to the -1, or 1 over e. And this is the only critical number, so it has to be that if it does have a minimum, it's going to occur at this x value. So a t-chart really isn't going to help, so let's connect back to that idea for a second. Okay, if I were to do a t-chart, and I don't have a closed interval, because x can only be defined for values greater than 0, I really wouldn't want to put 0 here because it's not an endpoint. And then it goes to infinity. The infinity doesn't really belong in here. So it's just going to be that it naturally has its lowest y value. All right, so we found the derivative, set it equals 0. We found one critical number. I'm going to just verify that it is a minimum by doing the number line test. And I could actually put like a parenthesis here and say that I'm not going to go further to the left of 0. Okay, this is where it gets kind of strange here. E to the negative 1. I need a test value that's smaller than e to the negative 1. Okay, well, I'm going to think about e to the negative 2. Because e to the negative 2 is going to be a smaller number than e to the negative 1. So let's go back and in the derivative, plug in e to the negative 2. So I'm going to do that right here. F prime of x equals 1 plus natural log. Now my input value is e to the negative 2. And remember, these cancel, natural log and e. Natural log and e. So this really becomes 1 plus negative 2. And that's going to be a negative number. And it's just because this exponent is smaller too. Smaller than negative 1. Okay, now let's look at a test value to the right of e to the negative 1. Like e to the 0, e to the first, e to the second, anything like that. I'm going to just test e to the 0. Okay, so go back up here, plug in e to the 0. All right, 1 plus 0, because these are going to cancel. It's going to be positive. So we've just verified that this is indeed an x value of a minimum. So that's the only minimum. It must be the exact, location where we have that minimum spot there. So we're asked to find the value. Let's plug in this x coordinate into the function back up here, and we'll get that answer. All right, well, I know that these cancel, so I'm left with negative 1. So f prime of e to the negative 1 is equal to negative e to the negative 1. Another way to write that is negative 1 over e. So that's what they wanted, the y value. If you wanted to give the full point, it would be 1 over e, comma, negative 1 over e. This being the x, this being the y coordinate of the minimum. All right, so this one was kind of unusual just because it asked for the minimum value. It almost makes us think that we should do the, the t-chart, but remember, it didn't give us a closed interval, so something just natural had to happen. So just proceed through, find the derivative, find the critical numbers, do the tests, and then from there, if you only have one, that has to be the answer. If they're asking for the value, plug the x value back into the original equation to get the y value. All right, let's fix something here on this question. I can see that we need to change this x to a 2. Okay, a function has a critical number at x equals 2. Well, at x equals 2, that means the slope is 0. We have a horizontal tangent. We don't know if it's a min or a max or neither, but that's what this means. The slope at 2 is 0. And then it goes on to tell us that the second derivative at 2 is 3. Second derivative is tied to concavity. It's positive, so that means the graph is concave up. So we have a horizontal tangent at x equals 2, and the graph is concave up at x equals 2. So what can we conclude about the function at x equals 2? Well, if these two statements are true, then f has to have a relative minimum. So my slope is 0. So if this is 2, if my slope is 0, I have a flat slope, but the graph is concave up, then that feature is a minimum at x equals 2.